Hi there, and welcome to the Week 11 lecture for GIS and Spatial Statistics. So today we're looking at point patterns. I'm Jonathan Marshall. I'll be taking you for the next 2 weeks. And we're looking at estimation and modelling of disease data today. Essentially, we're following on from where we were last week, looking at kernel density estimation. And we'll look at refining that a little bit with some adaptive kernel density estimates. We'll look at relative risk, and then we'll finish with a little bit of parametric modelling. So let's start by remembering what a point pattern is. Essentially, a point pattern is basically just a collection of locations across some region. And of interest to us is how the points are distributed across that region. So for example, are they scattered completely at random across the region? Or are they spatially clustered in some way? And potentially, is this spatial clustering important? Okay, and the tools that we'll be looking at today help answer essentially that third question. There's different ways that locations in space could be clustered. We'll mostly be looking at essentially the inhomogeneous Poisson process, where the spatial clustering is due to some underlying trend. We're not going to be looking at examples where the spatial clustering is due to some interaction between locations. So for example, if you have an infectious disease, such as COVID, for example, you wouldn't expect those locations to follow an inhomogeneous Poisson process, because of course if someone has it at a location, it's likely that all of the people around them are probably going to get it too. So your points are all going to be clustered because there was a case of disease there, not because of some underlying trend. Okay, so let's look at kernel density estimation in perhaps a little bit more depth than we have so far. So you remember that kernel density estimation of a point pattern essentially involves placing a kernel function at each location in the data set and then averaging over all of the kernels to estimate the density. So on the left here we have about 15 odd points, and we've got some circles around it indicating that I've placed an isotropic kernel, so a rotationally symmetric kernel on each point. And you can see that where the points are close together, those kernels overlap and sort of add together. Okay, so when we average across them, we get this nice smooth curve here, which is highlighting the density of points over in this region here. So in terms of the maths, it looks a bit like this. This can be a little bit daunting, but if you sort of break it down, it sort of makes sense. So this is a specific case of a kernel density. It's the one that's used most often, where our kernel has the form of a Gaussian. So that's like a normal distribution. So f hat, the little hat means it's an estimate. So we're estimating the underlying density f at a point x. And you can see that it's proportional to this thing here. So I've ignored the constant. There's a 1 over 2 pi or something or other out here to make it all integrate to 1. But what you can see here is that this first bit here is a sum over our locations our n locations, and then we've divided by n. So this is just an average. So all this says is we're averaging this stuff here. And this is our expression for the kernel. So you can see here that inside the kernel we have xi, which is our locations of our data. X is the point at which we're doing the estimation. And so you can see here that this is just a distance from x from the location that we're estimating to each of our points in our data set, right? The h then is just scaling that distance, right? So the h here is the bandwidth. That's the amount of smoothing we apply. So we're applying. So essentially this is just basically how many bandwidth are we away from each point. The further you're away, the bigger this number is, and because it's a negative, it means the smaller the exponential is. So the further you're away from points, the less they contribute to your estimate at a particular location. And that sort of is a natural way of smoothing, right? We're essentially locally smoothing. So we count the things that are close to us more than the things that are further away. Okay. Now, one of the key assumptions that we've been using so far is that h here is assumed constant across the region and does not change with x. Okay. And we'll see why that's a bad idea generally, or at least in many examples, in the next few slides. Before we get there, though, we need a couple of properties about this kernel density. Essentially, how good is it? And again, this is some bunch of mathematics here, but the idea is reasonably straightforward. The idea is that we can we can describe the performance of a statistic or of a statistical estimator in terms of how good it is on average, which is the bias. So it's basically how far away from the truth does our estimate get. So we have our estimator, our estimate f hat, and our truth f, which is and most of the time unknown. Then just how far away it is on average is the bias, right? And so you want that to be small because you want our estimate to be equal to the truth on average, right? But there's another way of describing how good f hat is, and that is it repeatable? And that's the idea of variation, right? So from sample to sample, do things change a lot? A good estimator would not change things a lot from sample to sample, assuming that sample came from the same distribution, right? So you've got this truth f, right, which is describes the true density of the locations, and then we take a sample from there, so we get a bunch of points sampled from that distribution, and we fit our kernel density to it. Then we repeat the process a bunch of times, right? And the variation that we get in our kernel density estimates, we'd like that to be small so that things are repeatable. So we'd like them to be accurate, but also repeatable, right? That's the two main things. And it turns out that there's always a trade-off between these two things. For a given sample size, you either have more bias or more variance. If you decrease the bias, you increase the variance, and vice versa, okay? And the reason for that is those two things combine together to give the mean integrated square error for our estimate here, which I think Mel would have talked about perhaps last week. Okay, so it's just the bias squared plus the variance. Okay, so a good estimate is going to have a small mean integrated square error, right? It's going to be close to the truth everywhere in our space, okay? On average, if you like. Okay, so to do that, we're going to need small bias and small variance, okay? Now, we can evaluate how big the bias and variance is, at least in the special case where our data set gets really large. Okay, so we can do some mathematics to work out what happens as the sample size increases. Okay, so essentially as the number of locations that we have in our region goes off to infinity, so we get more and more cases, then what do we expect to happen? Then what we expect to happen is that our bandwidth will get small, right? As we get more and more locations in our space, we can smooth a lot less, right? So our bandwidth h gets smaller. And it turns out that we can work out in that asymptotic case exactly what the sort of the leading order terms, if you like, of the bias and the variance are. And it turns out that they behave like this. So the bias scales with h squared, the bandwidth squared, and the variance scales with 1 over n times the bandwidth squared. Okay, so essentially what this means is that as h is getting smaller, the bias is getting smaller even faster. Okay, and the variance is possibly getting smaller, but it depends on n. Okay, now of course we need both of these things to be small. Okay, and you can see here that if h is small, you're going to have small bias, right? Because if h is small, then h squared is smaller. But if h is small, then we've got h squared on the denominator here. So the denominator is getting small, so the whole thing's getting big. Right? So that's where the trade-off between bias and variance comes. It's just that as we reduce the bandwidth h, we get less bias, so we're sort of more accurate to the truth all the time, but there's a lot of sample-to-sample variation, right? There's a lot of variance. Right, you can imagine sort of in the limit, if you like, if we set h effectively equal to 0, then basically all we have is a little spike on each of our locations. Right, so if you compare two samples from the same distribution, you'll have two sets of spikes, and they won't be in the same location at all. They'll be different, right, because the underlying samples are different. And so you'll have massive variance, but each of those spikes is correctly sort of, on average, is going to be really good, because it's going to have low bias. Okay, so you remember that the mean integrated square error was the bias squared plus the variance. So essentially that's going to be of order h to the 4, h squared, and plus this. Okay, and in order to have a good estimate, essentially we want those things to be of the same order. And so we want order h to the 4 to be about the same as order 1 over n h squared. And we can sort of balance these two things out by noting that that happens when h is n to the minus 1/6 power. So this is the 1 over the 6th root of n. Okay, and 1 over the 6th root of n. Okay, and 1 over the 6th root of n is 1 over 1/6. So this is the 1 over the 6th power. So this is the 1 over the 6th root of n. Okay, and 1 over the 6th root of n is 1 over 1/6. So this is the 1 over the 6th root of n. Okay, and 1 over the 6th root of n is 1 over 1/6. So this is the 1 over the 6th root of n. Okay, and 1 over the 6th root of n is 1 over 1/6. So this is the 1 over the 6th root of n. Okay, and 1 over the 6th root of n is 1 over 1/6. So this is the 1 over the 6th root of n. Okay, and If it's that, then the mean integrated square error scales according to n to the power of minus 4 over 6. Okay, so this is meaning that as n gets large, the mean integrated square error gets small. That's exactly what we want from an estimator. As we get more data, our kernel density estimator gets better, but it doesn't get better as fast, if you like, right? There's a trade-off here. It's not as if, by doubling n, we get twice as good. Instead, by doubling n, we only go sort of 2 to the minus 4 over 6, which is not half, right? It's something worse than half. So it's perhaps we only do 2/3 as good or something. Okay. Compare that to, for example, the sample mean. So in a standard statistical setup where you're estimating a population mean with the sample mean, then the error in the sample mean goes to 0 with 1 over n, right? So each doubling of the sample size, the mean square error halves. Okay, so that's a much better relationship than this one. And that basically comes down to the fact that we're doing a lot more work with a kernel density estimator. Instead of estimating a single value, you're estimating a function across a surface. So this is like an infinite dimensional thing. It's a hard thing mathematically to deal with. But it turns out that we can do better. And we can do better using an adaptive kernel density estimate. And the idea is simply that we allow the amount of smoothing to change as we go across space. And this is good because point patterns are very rarely homogeneous, right? They're not constant across the surface. If they were constant across the surface, then they'd be boring. Okay, and we could just fit a flat intensity, and we'd be done, right? It's just complete spatial randomness. We never have that in any interesting example that we're dealing with. Most point patterns are highly heterogeneous, particularly things when we're dealing with people. So, for example, in New Zealand, 87% of New Zealanders live in towns and cities. Right? So only 13% of New Zealanders live outside towns and cities, and of course the vast majority of the land area is outside towns and cities. So we've got large areas of New Zealand with very few people, i.e. where the population is sparse, while we've got a few areas in the cities and towns where the population is very dense. So if you were looking at locations of people in New Zealand, using a single bandwidth to cover that region is going to be really bad because you're going to require more smoothing in the areas where the data are sparse, where there's no people. You want to smooth that over because you're never going to get many points there. Whereas in the cities, you're going to want a lot of detail, right? Because we know we've got lots of data there and we want to pick out where that data is, okay? And so we want to smooth less in the cities, in the dense areas, and we want to smooth more in the sparse areas. So a kernel density estimate with a common bandwidth across the entire region is going to essentially undersmooth the sparse regions and oversmooth the dense regions. So we're going to get no detail in the cities, and we're going to get sort of blobs in the sparse region and in the rural areas where we're undersmoothing. And the solution is kind of obvious when you think about it. It's to allow the bandwidth to differ across the region so that we can smooth over the sparse regions by smoothing more, and then provide detail in the dense regions, in the cities, for example, by smoothing less. Okay. Now, of course, the question is, how do we do this? So it turns out that that it makes sense to change the bandwidth based on the density of points, right? That's just what we've basically been talking about. In areas where there's lots of points, so where f of x is high, right, in terms of density, we want less smoothing. In areas where points are very sparse, so f of x is small, we want more smoothing. Okay, and it turns out that that scaling with the 1 over f to the 1 over the square root of f basically is the optimal way of doing so. Okay, so Ian Abramson showed this, and I think it was about early 1980s, 82 I think. Essentially that if you scale the bandwidth to the 1 over the square root of the density, multiplied by some average sort of global smoothing parameter, so you can still alter the smoothing overall, it's just that within each of the regions that's then scaled up or down depending on the sparsity of the data. when you make that particular choice, then your bias reduces to order h to the 4. So you remember before we had our bias order h squared, okay? Now it reduces down to order h to the 4. So that means as h gets small, the bias gets small really fast, okay? And it turns out that this benefit happens while not sacrificing variance. So the variance of the adaptive estimate with this particular formulation is the same as the variance of the estimate with a fixed bandwidth. So the variance is unchanged, but we have an improvement in the bias. And so when that happens, h0 can now scale with n to the power of minus 1/10. So previously it was n to the power of minus a sixth, I think. Which basically means that the mean integrated square error now goes to 0 faster. So instead of n to the minus 4 over 6, it's now n to the minus 8 over 10. Okay, so we get a better performance than the fixed bandwidth kernel density estimate. So not only does it make sense, because most of our point patterns that we see are going to be heterogeneous, so we're going to want the smoothing to change across the region, but it also, for free, gives us a better estimate in terms of the bias. So the bias is reduced, therefore essentially we can get a better estimate with a bit less data, is what it comes down to. Now the disadvantage, of course, is that in order to know what the bandwidth should be at each location, we need to know what f is. And of course our whole thing here is estimating f, right? This is why we're doing the kernel density estimates, because we don't know what f is. So we've got to know what it is before we can know how to estimate it. It's kind of a weird backwards thing. A circular thing. We're never going to get anywhere, right? So what we do is we do it iteratively. So what we do is we say, okay, so we don't know f at the start, so we don't know how we should adjust the bandwidth. So all we do is we use a fixed bandwidth as a starting point. Generally, it's better to use a small bandwidth for that, perhaps a little bit smaller than you would usually use. You want to undersmooth a little bit. And that gives us a pilot estimate, f hat p, okay? And we use that in this formula here. So we take f out because we don't know what it is, and we replace it with f hat p, and that then gives us what the bandwidths for each of the kernels should be. Okay, and then we then fit the adaptive estimate using those adaptive h's. You could potentially do that process again. So once you've got an adaptive estimate, you could then plug it back in here and repeat the process. But generally, one step is plenty. It does the trick. Okay, so the only problem here is we have to end up estimating two bandwidths. And I know that Mel talked a little bit about how sort of optimal bandwidths can be found. Right, so how do we do this in practice? Well, in practice, we can use the SPA package. The bivariate density function in that implements the adaptive kernel density estimate of Abramson. And it takes a standard SPATStat point pattern object, a PPP, and can do both fixed and adaptive estimates. So the fixed estimate, I think, just calls density.ppp, which I think you've used before. The fixed estimate just needs h0, which is basically your bandwidth. The adaptive estimate needs both HP and h0, but by default, the pilot bandwidth is just set to whatever global bandwidth you feed it. And you can use adapt to switch between fixed and adaptive estimates. It defaults to false, which is a fixed estimate. Okay. So we're going to look at the same data set that I had before, which is just 15 points sampled from the PBC data set, which will be detailed a little bit later on. So here are those same points, 15 points, okay, across our region, and we're going to do a fixed estimate and an adaptive estimate. So here's the fixed intercept. So I feed it my cases, right, which is a PPP. I feed it a sample bandwidth. So I've just picked 10 because it looked okay. There was no rationale for that other than it didn't look silly. And I've told it that adapt is false, so it gives me a fixed estimate. And then I'm just using ggplot here, but you could just plot that, right? You could just go plot fixed, and it would come up with a map that looks a bit like that. And as you can see, it correctly highlights the areas where we have high density, but you can see we've also got a blob here, up here, which has been highlighted a little bit, right? We've got some much lighter color here. So we've got under smoothing here and potentially over smoothing down in here. Okay. So switching to an adaptive, so we just switch adapt equals to true, then we get this picture here. So you can see just if I just flick between the two, I'm now got much more smoothing in the countryside there. I'm assuming this is the countryside. In the area where we don't have any points, okay, it is now smoothed over, and we actually have a little bit more detail in here, okay, in terms of the shape of this raised region here is a little bit more defined. Okay, so that's adaptive estimation. How it's actually working, of course, is it's changing the bandwidth. So I could pull the bandwidths out and plot those, and you can see that I've got a much larger bandwidth out in this area here where the data are sparse, and I've got smaller bandwidths through here where the data are dense. Okay, so that's adaptive bandwidth estimation. Now this data here actually comes from a data set of cirrhosis. So it's essentially cases of disease in northwest England. So this is an area of northeast England, I think it is. This is an area of northeast England, and these are cases of disease. Okay, and whenever we've got cases of disease, what we're really interested in is places where the rate of disease is higher than we would expect. Okay, but plotting the location of disease observations is no use for that, right? Because disease observations are dependent on, in order to have a person with disease, you first need a person, right? So a map of people with disease is very, very similar to a map of people, okay? So we've always got to consider what is the denominator, if you like, right? What is the thing that we're looking out of? What we really want when we look at looking at a map of disease is we want to know where is there more disease as a proportion of the population. Okay, so per capita is essentially what we want, right? And as we know, New Zealand is always best per capita. So the data that I was talking about before come from this data set here, where we have a distribution of cases of disease. This is the PBC data set in the SPA package. And we also have a set of controls. So this is a population, or sort of a pseudo-population, sampled from the true population. So it's not all of the population. There's only 3,000 people or something compared to, I don't know how many people are in this region, but it's probably hundreds of thousands. Okay, but the idea is that we can use the sample of the population to get an idea as to where people are, and we can then compare that to the distribution of cases. And you can see that they're kind of similar, and that most of the cases are over here, and that's where most of the people are. But there's possibly some differences in that the number of cases out here is actually maybe a bit lower than the number of people. It's a little bit hard to tell because it's, all of the points are sort of overlapping. Okay, but there's possibly some areas where there's a different density of cases. Maybe here, this density of cases is actually quite high compared to the density of controls. So essentially what we do is we estimate risk by working out the density of the cases and working out the density of the controls and then taking the ratio. Okay, so we look at the relative risk at a location X. It's often denoted by rho, and it's just the ratio of F over G, where F is the density of cases and G is the density of non-cases or controls. Okay. And all we do is we use a kernel density estimate for F and a kernel density estimate for G, and that then gives us an estimate of rho. Now, we often look at rho on a log scale, and the reason is that a relative risk of 2 means that F is twice as big as G, while a relative risk of a half means G is twice as big as F. And we want those to be represented sort of the same distance away from neutral point. The neutral point would be when F and G are the same, right? The relative risk would be 1. And of course, the distance between 1 and a half is not the same as the distance between 1 and 2 on the raw scale. But if we take logs, then it is. Okay, if you think about it, if you take a log base 2, then this would be 1 on the log base 2 scale, whereas this would be minus 1 on the log base 2 scale, and relative risk of 1 would be 0 on the log base 2 scale, right? So it's symmetric. It's also useful to do that on a log scale for computational reasons. essentially you're dividing by something that could get quite small here in G. So if you take the log first, it's a little bit less sensitive to that. Okay, so we can do this by essentially smoothing the numerator and the denominator. So we're going to smooth the cases and smooth the controls from the PBC dataset, and then we're going to take the ratio. So here's some code for splitting that. So the PBC data contains both case and control in the one dataset. It's what's called a marked point pattern. So you've got the locations X and Y, and you've also got, is it a case or is it a control? So the split function helps you to sort them out. So we've got cases and controls. We could plot them from there, which is what I did back there. And we can work out a bivariate density estimate for both of them. Adaptive estimates of both of them, which I've saved. Notice I've used the same global bandwidth for both of the cases and controls. In this case, we have about 760 cases and about 3,200 controls. So if you were just looking at one or the other, you would tend to use a smaller bandwidth for the controls than the cases because you've got more of them, right? So you've got more detail, you can get away with a smaller bandwidth. But because we end up estimating a ratio, it turns out to be optimal to choose the same bandwidth for both. So that might mean that you end up over smoothing the controls a bit and under smoothing the cases a bit in this example. But it's sort of what happens is the first order bandwidth sort of cancels out in that ratio. Okay, in the bias, if you like. If you look at the bias for rho, it turns out that the order H term cancels out if the bandwidth is the same on the top and on the top and bottom. So once we've got those two densities, we could plot them. I think we've got them here. Okay, so you can see here that maybe there is some evidence of them being different, right? And that the shapes that you get in the controls here seem to be sort of three main population centers with maybe another one down here. Whereas in the cases, it tends to be focused in this one and maybe this one here, right? There's not the cases down here and not the cases down here than we would expect given the controls. So it does seem that as though the distribution of cases differs a little bit from the distribution of controls. We can combine these with the risk function from the SPA package. So you just throw your case and your control density in and it gives you a risk surface. And that's what this surface here is. So again, this is on a log scale. Okay, so 0 means a relative risk of 1. A negative number means you've got more controls in that location compared to the cases. And a positive number is where you've got more cases compared to controls. Right, so the red here is where we've got more disease, and the blue is where we have less. Okay, so you can see that there are some areas of heightened risk, potentially across here and more obviously in here. Okay, where we got this darker red color. The risk isn't huge, so it's a relative risk of less than 1. So on a log scale, that's about 2 or something like that. So it's like twice as many cases as you might expect in some of this region, given the population. Okay, now what we'd expect, of course, is that if we took a different sample from the same region, so we came back perhaps another year, and we took the cases from a different year and looked at the same plot, we might expect to get something slightly different, right? There's going to be noise associated with this estimate. And so we might want a measure of statistical importance, which we can get from the SPA package using a p-value surface. So you remember, a p-value is essentially how extreme our observation is compared to what we'd expect by chance if there was nothing going on, right? That's essentially what a p-value is. And so in the relative risk scenario, it's essentially what we do is at each location we estimate, well, how likely is it that we got a relative risk of, say, 2. For example, if we're up here, we've got a relative risk, we've got a log relative risk of about 1. What's the chance of having a log relative risk of about 1? Or worse, if in the population at that location, the relative risk was in fact 0. So what's the chance of observing a value as large as 1 in a sample, just by sample to sample variation, if there was actually nothing going on, right? And so we get that p-value estimated at every point. So the tolerance function in SPA is used for that, and it can either be done using asymptotics or using Monte Carlo simulation. And so this is the idea, right? Here's our surface here, our risk surface that we estimated earlier, and this is the corresponding p-value surface. Okay, so you can see that in most of the areas, the p-value is 1, or is large, essentially. So this is saying that what we observe here, all of these differences, are just chance. Okay, now this is a one-sided p-value, I think. So this is only assessing is the risk big. So of course, in all of these blue areas, the risk is not big, so the p-value is clearly 1, right? In the red areas, in many cases, the p-value is quite large. So we're in sort of this blue color down here, and so there's not much going on. But in some areas, we're getting into this green and yellow where our p-value is getting quite small, right? So this yellow region is saying that there's a high chance that it's extremely unlikely, essentially, that this observation here being high is just due to luck. Okay, so there's probably something going on. And perhaps a better way to do that, to do this sort of thing, because you have to look at two plots and sort of decide, you know, is it large here and is p small? You sort of have to go back and forth. A better way to do it is perhaps convert this plot here to contours and slap it on top of the other one. Okay, so here you can see that there's this region here of heightened risk, and that seems to be statistically important, so worth investigating further. Okay. Right, so that's essentially non-parametric modelling of point process data. Okay, what I mean by non-parametric is that there's no underlying model here. We're not saying that the disease risk is dependent on anything at all. We're just sort of saying, here's what our data looks like, please smooth it to give an estimate of what the density is. Okay, we're not modelling the density using some covariates or anything like that. But we can do that, okay? And so that's what we're going to move on to now. So up till now, our KDEs are basically non-parametric estimates. So essentially, it's like doing a box plot or a histogram, right? It's basically the same idea. You just want to give me a graphic of the underlying density, an estimate of what the underlying density looks like. So it's similar to just estimating a mean. Okay. The alternative, just like we can model a mean in terms of covariate with a linear model, we can do a similar thing with a point process. So we're going to model the underlying intensity or density of the point process lambda, which can change with x, using some parametric model. So so our model might depend on the location x and or on a bunch of other stuff that we might have available to us. And we'll see this in the workshop a little bit. So essentially this process that we'll be looking at assumes that the points arise due to a Poisson process with some intensity lambda. Okay, so that the number of points that we observe in an area is basically comes from a Poisson distribution with some rate capital lambda sub a, right? So different regions A have a different rate. Okay, and that capital lambda is just the integral of the intensity. Okay, so that's how it comes up. This is just the expected number of points in a given area. It's just the integral over of the intensity over that area. And we can fit these models plus some fancier ones, to be honest, in using the ppm function. Okay, so the models that we're going to be looking at are going to assume that that we have a inhomogeneous Poisson process. So that means that the intensity of the points only depends on where they are and some underlying trend. There's no point-point interaction going on, right? So this is not useful for modelling infectious disease, where the infection can go between people, for example, because, of course, with an infectious disease, if you've got disease at a location, then you expect other cases of the disease around that location. So it's not for modelling that scenario, although the ppm function itself can model that scenario. So there's more general processes than Poisson processes, such as Gibbs processes and log Gaussian Cox processes and all these shot noise processes and all these other ones that can be used in those scenarios, but we're just going to look at the simple one where all we're modeling is underlying trend and we assume there's no point-to-point interaction. So this is good for non-communicable diseases, such as things like cancer and stuff like that, or foodborne illnesses like cryptosporidiosis or giardias or campylobacteriosis or salmonellosis and so on. So how do we do this? Well, the simplest thing that we can do is fit a homogeneous process, right? So we assume that the cases just arise due to some constant function across the region. So it may as well be a rate of 1, right? This is again looking at the cases data. We've loaded the SpatStat library to pull out ppm. And the ppm, essentially, if you've used any of the R modeling functions before, you might have seen LM or GLM. This is basically the same syntax, right? And that you have a formula object with your points on the left, and because that's your outcome variable, and the things that you're modeling with on the right. So when we fit this, we get some output spat out, right? We get an estimate for log lambda. Notice that it recognizes that it's fitting a stationary point process. Okay, so it's a homogeneous one. It's not changing across space. It's constant, and it's giving us an estimate for log lambda, which is the log of the intensity. So the actual intensity is going to be e to the minus 2.357, which is 0.0947. And this, of course, is just the expected number of observations per unit area. So in our case, we've got 761 cases in this data set, 761 locations, and the area is about 8,000 kilometres squared. And so we'd expect our intensity to be 761 divided by that 8,000, which is in fact that rate. Okay, so that's the simplest thing we can do, is fit a homogeneous point process. Now, of course, we know that the case data here is not flat across that surface, right? It was concentrated down in the sort of the southeast, or in the east at least. So we could instead fit a inhomogeneous function, right? So what happens if we include x and y coordinates, if we allow the intensity of the cases to vary by x and y? Okay, so we just put our covariates in, x and y, and we add them together. This just basically means that x and y both contribute to the log of the intensity. And then we get coefficients for x and y. Okay, we can see, so some of you wouldn't have seen output like this before, so let me explain it. So this is our estimate. So this is basically how much log lambda, okay, because we're looking at the log intensity, how much log lambda increases as x increases. So that would be as you move east, x would increase. And as you move east, lambda would increase. This is the standard error of that term, so essentially it's a measure of how precise it is. And this is a confidence interval, so a 95% confidence interval. So we're 95% confident that the coefficient of x is somewhere between 0.074 and 0.086. So either way, it's well away from 0, and so this is basically a measure of how important that is. More stars, more better. Okay, so we can see that x is important because we've got stars, okay, and that it's increasing because we've got a positive estimate here. So that as you move towards the east, so as x increases, gets bigger, the intensity gets bigger. Whereas y is not important. So as you change y, lambda doesn't really change much at all. It could be getting smaller, okay, because the coefficient of y could be negative, or it could be positive. So as you increase y, then lambda could either get smaller or bigger. We don't really know. So it probably doesn't have any effect, right? So we could, I'm not sure if I've plotted that. I haven't plotted that, but essentially what you'd expect is that if we go back and have a look at our point pattern, there's our point pattern here. So as I expect, as I go towards the east, I get more cases. Okay, so that's all that's telling me. So all I've got is a flat surface, essentially, that's increasing intensity as I move east. It doesn't change much as I move up and down. It makes sense given what we've seen. Okay. Perhaps a smarter thing to do would be instead of just putting X and Y in, we could actually put in some covariate information. So in this case, the only covariate we have is where people are, okay? But we could use that, right? And so here we're pulling out the control data. We're fitting our bivariate density to it, right? So we're fitting an adaptive kernel density estimate. We're manipulating it so that it's a pixel image. And then we're putting the log of that pixel image into the formula for ppm, formula for cases. So we're saying our log intensity of the cases is going to change based on the log intensity of the controls. That's why the log is there, because of course we know that the intensity of the controls and the intensity of the cases should be somewhat related, because both are to do with where people live. Right? So this is essentially controlling for the denominator. Okay, so when we do so, we find that we have an increasing estimate. So as the density of controls gets bigger, the density of cases also gets bigger, right? So as in areas where there's more people, there are more cases, right? And that is, of course, highly important. So this is a very boring model in terms of it just tells us that population is important for describing where cases of cancer it's not actually cancer, where cases of the disease will be. It's not a particularly useful model in that it's not actually evaluating anything, any hypotheses other than, you get disease where you get people. You get people with disease where you get people. Okay. In the workshops, we'll be looking at some slightly more interesting cases where we actually have some covariate information that we can put in. So that's it for today. Essentially, 3 things to remember. Consider using an adaptive bandwidth, particularly if the point pattern is highly heterogeneous. If modelling a disease, remember that the denominator is super important. Okay, so use things like relative risk or per capita measures are important. And the last thing is that if you have a specific hypothesis, perhaps some correlation with some covariate, then you can model it using ppm.